Good afternoon to all. On behalf of Department of Electronics Engineering, I welcome our today's second session speaker, Mrs. A. Navis Nirmal from Aptiv TCI Bangalore. She is a senior software engineer. Hearty welcome to you, ma'am. Now I invite Dr. V. Satish Kumar sir to give an introduction about our today's speaker, Mrs. A. Navis Nirmal. Over to Satish sir.
Thank you, ma'am. It gives me immense pleasure in welcoming Mrs. A. Navis Nirmal, Senior Software Engineer from Aptiv TCI, Bangalore. So, ma'am is experienced in automotive industry, working in radar front-end development. So, she has completed her PG from VLSI Design and Embedded Systems, MIT, and UG from Sri Sairam Engineering College. So, hearty welcome to you to this Atal FDP program, ma'am. So now you can hand over the session. So the topic of presentation is testing for ADAS and automotive embedded firmware development. Thank you.
Thank you. Thank you for the warm welcome and good afternoon, everyone. I'll share my screen now. Is my screen visible?
Yes, ma'am. It is visible.
Okay. Yeah. Thank you for giving me the opportunity to present the session today. And this is Navis Nirmal here to present testing for ADAS and automotive embedded firmware development. So as we all know, ADAS is a most live technology currently we are all experiencing on roads, and I am being from Aptiv TCI Bangalore, which is an global technology company which designs, develops, and manufactures the software and hardware. Where I particularly worked in radar front end software development, and that solution is to enable a safer, greener, and more connected future of mobility. And our solution to help the automotive OEMs around the world to create vehicles with advanced safety features, electrified architectures, and intelligent connectivity. And as I've already mentioned, the industry market platform, whatever we mention, is always evolving. And we have to adapt to the new technologies and new uh, algorithms or whatever the way of testing to ensure our safety is our priority. So Aptiv's deep understanding on global regularity requirements, we all have a set of requirements to be followed before we are giving a software or hardware to be implemented on road. And we are ensuring to understand the requirements and the roadmaps to ensure the platform is ideally suited to current and also for the future ADAS needs. So whatever we are writing now, it need not to be only fine to work for this year or next year like that. It should be adaptable for the further ADAS improvement itself. That's how the software to be written, and that's how we are all working for. And Aptiv software architecture is scalable and it's flexible to adapt for the future needs also, future resilient and operating in a variety of driving conditions. The driving conditions, what I mentioned here is a weather conditions also, since as we work for radar front end, the radar should be suitable for getting the environmental measures in all the weather conditions. Since our customers are wider, we have to be adaptable for even a variety of driving conditions with the reduction in complexity and cost with the increase in efficiency. That is our motto to write or to implement or to give the software developed. Okay, so as in topic, we all know ADAS, it's an advanced driver assistance systems. As as in the title, as in the definition, assistance is what we are creating something which assist us or help us to operate the vehicle very safely. And human errors are unavoidable. This is to reduce the risk of human errors, not like eliminate the complete errors or mistakes or things happening day to day. It's to create the software or hardware for the vehicle safety, which reduce the risk of human errors. And ADAS uses the sensors and cameras since we need environmental information to be gathered. With that, we will be simulating and we are giving a warning or intimating a driver or user to be in a control or to avoid scenarios which is bad for us and our vehicle also. And so we are mentioned here as it uses the sensors and cameras to get the information and to inform the user in a sense all the customers of us who is driving our cars. And sometimes it informs the user or it will automatically acts itself. That is what is a levels of cars what we were providing. L0 to L3 we were giving. Some cars it's like hands free, eyes free, like that we have terms, no, as like it acts itself. It need not to be giving from the interference of a driver to control the car. It itself will take care of the things. And there are so many ADAS features nowadays in market. And here I'm not gonna explain like what is what for each thing. We all know like pedestrian detection, lane departure warning, blind spot detection, and driver drowsiness monitoring, adaptive cruise control, automated parking, and adaptive headlights. These are few features I have listed here. Even there are more. As per the customers for the company, they will be providing required features from the customers. So here, as we all know the things like what we are controlling over these features. Uh, Automated parking is most of our cars on road is having the automated parking. Even L0, L1 levels are having the automated parking features, where it automatically, when we select the spot, it will direct our car to park at the space. And pedestrian detection and blind spot detection are just to avoid the collision to the pedestrian people or another vehicle in the blind spot areas of our vehicle. Just to avoid our collision, these are the features which warns us like there is a people, there is an object detected. Just avoid such lanes. And lane departure is like to not to drift from the lane where we were driving. So lane departure warning is around that. And driver drowsiness is even an interesting topic. Like it uses a camera, it keep on monitoring the driver, and that captures timely data. And it says like if it is out of control, if it is going out of a control, and it feels like a driver's drowsiness is noticed for prolonged time, and so it will intimate and it will automatically reduce the speed and velocity of the car. And adaptive cruise control is also the same. It will automatically auto control the speed of the car. And adaptive headlights, it's all we know. The traveling in nights is headlights is the biggest issue, or however we can mention. Likewise, the adaptive headlights, which feels like it also gives the uh, driver to know the curves and cuts or the darkened areas where we can uh, adjust our headlights intensity and also the direction, uh, which is under this feature. So these are very minimal features I have listed here. There are even more. And next we will go for the testing for ADAS. As we have seen like what is ADAS and what are those features available under the ADAS. Uh, as the today's topic is testing the ADAS. As I'm giving certain features to my customer, it needs to be tested from my end, like whether it is working properly as expected. Am I giving a right software, a right hardware? Is it reliably related to both? And or my customer is fine to use it in a proper way. So what is testing? This is a generic explanation as we will see it in uh, Google. Like what is testing? Simply a testing is to try, use or examine something carefully to find out if it is working properly or what it is like. So as I'm giving a thing to a car which will be on road, which holds a full lives, I need to examine everything one after other whenever my development from the scratch till the developed software is handed over to the customer. So this is a basic of testing. And in ADAS, there are so many methodologies. In Crunch, we can say it as X in loop methodologies. So here X in case we can say it as software in loop, hardware in loop, vehicle and hardware in loop, and vehicle or driver in loop. There are so many methodologies to test the ADAS, and it differs with each feature how it will be tested. But here I'm gonna explain like what are the basic testing we will be taking care before handing the software to the customer. The first one is still the software in the loop testing. It's the best way to test some components of ADAS software. It's like it can't be said as a unit test. We will be doing a functionality of the software. It is another way where we can do like we will create a simulated environment. We won't use the hardware directly or any. As I am working for radars, I'm not using a radar directly to the testing. I'll be simulating what is expected or the environment. Everything is simulated, and by this I will be linking my algorithms. Whatever I'm using, that algorithm will be correspond to a certain vehicle hardware. If I'm working for sorry sorry if I'm working for ECUs, the radars, I'll be taking that particular simulated algorithms, and I'll be using that, and our code performance will be checked against that simulated environment. We will not be using our actual hardware parts. None of my harnesses or ECUs or radars or none of my the parts of cars will be used. It's only a simulated environment. It's within a PC. So I'll be ensuring the basic level. As we all know, SIL and HIL, software in the loop, is the one which we test in the beginning of the development, and hill will be at the end of the development. I mean, almost at the end of the development. Once the hardware is ready and we incorporate or embed our code into it. So next is a hill, hardware in the loop. So now it's a popular method of ADAS and autonomous vehicle testing. So we all in our companies, we will be doing our basic bench setup, not as one whole car to be tested, but we will be keeping one small bench setup with our rear sensors and front sensors mounted in a small box or somehow. And that's how this test will be taken care. So here it's an approach which will be using real-time simulation with the vehicle hardware. So we will be having our parts or a component, that particular single component removed out of the car or before the molding. We will be keeping it in a bench setup, and we will be doing this hill test. So it's a flexible testing because we know like how the sensors is receiving and giving our data. We can block simply with that, and with that ECU for a blockage test, or for the weather condition we can make it in a temperature chamber test. Those and all will come over this hardware in the loop, and it is great for prototyping also. And here, as I mentioned, the hill simulation is that real hardware is combined with the simulated components. Like we will be having our real hardware in hand, and we will be running our simulated codes and over it, algorithms over it. So the next is driver in the loop. So here the driver will be there, environment will be virtual. So the setup and all will be there, driver will be driving. This is to uh, get the input from the human drivers, just to improve the development of ADAS. And mostly the hill and sill is where I have worked on. Driver in the loop is like once after that, once the manufacturing is there, we can use such scenarios. So here the real people will drive the simulated vehicle that has a controls like a real vehicle. Like we all have in some exhibits and all, we will have a simulated things to be tried out. Right. Likewise, we will be having a simulated vehicle, and it also operates in a virtual environment, which is a log we have collected in multiple wider areas where that those can be experimented, and we can get to know like what exactly can be done for adjusting our code or to improve our code. Likewise, we can get input from here. And this is a vehicle hardware in the loop. This is called vehicle. It's a multi-agent simulation because here we will be having our own radar mounted vehicle as one, and another one as a robotic platform. We will be having another target vehicle or the host, another vehicle, the approaching vehicle or residing vehicle as a robotic one. We will be using that, and we will be changing our required expected changes from the environment from that artificial robotic platform. That can be done, and in our host we will be receiving those things, and we will be testing our code accordingly, whether it behaves as expected when there is approaching vehicle giving such uh, inputs or measurements. So by using this vehicle method, we can use the vehicles, we can test the vehicle's performance with targets. A target is where our robotic platforms or robotic, another car kind of robotic setup we will be having, which will be simulated. And this is a vehicle in the loop. Here, real autonomous vehicle will be there, and a human driver also will be there, and environment will be simulated. This is another kind. And here, the virtual traffic means here all our simulated environment means here this is also our part. We will be giving multiple cars or all kind of objects. We will keep stationary, the pedestrian and the running object likewise. So it should evaluate everything and it should behave as expected. That is how the vehicle in the loop will work on. The vehicle drives in virtual traffic either by itself or controlled by the driver when needed. So that kind of testing will be done here. It is used for studying the human behavior, because here, as in camera testing, as we have seen earlier, the drowsiness things and all, we need the car also to look over the driver's attitude or whatever behavior to get the feed for the expected results of code. Okay. So these are all, as I mentioned, these X-fin loop methodologies, software, hardware, vehicle and hardware, vehicle driver are the overall generic way of, can't be said as a generic. It's all the way of testing all our ADAS features. So it's all the part, like the way of testing, we can say. There are multiple ways, and these are the ways to test our ADAS features. And now I'll move to where I am particularly working on the radar front end. So here I am working on the department which is Mimic. Uh, Very beginning where our data acquisition is happening. Mimic software is where I'm working. So here is where all our data acquisition is happening. It means like we will be mounting a radar, and as we all know, radar is like it will transmit and receive the data. So the radar front end means it's a component of radar system. It is responsible for first part of receiver chain. So it means like whatever the processing later, it's all depend on the very first data acquisition from the environment. So uh, here three fundamental quantities we are measuring with radar: the range rate, and azimuth angle. And the hardware, what the hardware here in a sense, the ECUs, the electronic circuit units, what we are mounting, the hardware produces a frequencies which is proportional to the ranges of targets. So with the frequency is the most important thing we will be noting, and with that what our system will react to it. So range rate and azimuth angle is mostly the major quantities or measuring calibration which we got from the environment. So just to define what is what, range is a distance to the target. So if one of this is my car in a sense. If I'm the vehicle or the approaching or receding, whatever, the distance to the target, how much I'm in a distance from that target is what is a range. And range rate is how fast is the distance. It is like how fast is the distance is a velocity, the relative velocity between the target and host. That measured is called range rate. And azimuth angle is how the angle of a target and the host differs. Though that means like a azimuth angle. So these are the three datas. We will be mounting our radars in front, rear, and now even in the door side, we can say like there also we will be mounting. So there are almost the short range radars, long range radars. There are different differs upon the range itself, because how much ever you want to keep a range to cover your environmental measurements or to observe, that is how the mounting also will happen. And as per the mounting is what the azimuth angle will be grabbed from the environment. So these are the three major measuring things out of the environment. And one another term we can understand is chirping. So as we all know, we will be giving a signal and receiving a signal. So there will be two signals. Consider this as a signal. We will be transmitting a chirp. So continuously, my car where the radar is mounted keep on sending a uh, signal that is called the transmitted chirp, and we will be receiving a chirp from the uh, nearby cars, which is a received chirp. So the receiving chirp will differ as per the movement of the car. So this is to understand the frequency, how far my car is to the target. That's how we can understand where am I. So a technique that uses a frequency coded pulse to create a narrow pulse, which means a chirp with a high peak power. This process is called the chirp pulse compression and is used in radar and sonar systems to provide detailed range resolution. It is not only in radar, even in sonar, wherever it's used. The chirping is a concept we all have to understand. So by knowing the frequency continuous reception chirps, we can understand like where our target one is, target two is, like that. So after that chirping, we will be having this DFFT, RFFT, first pass, second pass. Likewise, we all will filter it to detect the object. It is not only like receiving multiple chips. Then we will process it in DSP and concised to it to a one single object, a valid object. Not simply all need not to be observed, right? Even a stationary object, a post pole, that and all need not to be observed. So we need to find the true object or a valid target. That's we will get from the FFTs. And this is a processing in DSP. Uh, Here, as I mentioned, when we were having a multiple targets, more targets, the DSP separates out and identifies the many different frequencies in the signals. It knows every frequencies. As per the range and range rate, the frequency will differ. So it thereby identify the different range rates and azimuths. With that, it will process it. So this ADC, what I mentioned here is like a signals what we are receiving, and it will go for range FFT, then Doppler FFT. Then this is a process what we were doing as in a building blocks. So this is a look processing, and this is a alarm, and this is a first pass and second pass. It will all go through, and angle finding will be there. These are all the process it will go through, and we will be getting a. It is not only for finding a valid object, but also to give upon the angle issues or azimuth issues. Also, we will get find within all these process. And I'm not gonna explain all this process here. These are all the same conceptuals what we have used to study. And here it's a crisp, I can say, like FFT is it finds a low frequency in the signal and places the result in the appropriate frequency bin. So it will be arranging those detections in a frequency bin, and we will be having a Doppler bin also. So first we will go for the frequency bin. It will get the frequency signals and it will put in the frequency bin. Then what is DFFT frequency shift is, consider here I have mentioned three different scenarios. First, consider two cars which is going in a same speed. So here, a vehicle with same velocity as a host returns same frequency as a transmitted signal. So if I'm sending a signal with the same speed, I will receive a signal. So there will be no difference that radar waves will not be disturbed. So I'll be getting the same frequency. And in case of approaching vehicle, so if my vehicle is approached by another vehicle, approaching vehicle returns a higher frequency because our radar waves, what we send, the transmitted wave will be compressed at that point. Our car is approached by another car, and the radar waves, what we send, is getting compressed. So here, the higher frequency we will receive. By that, it is it gives a range, so we can understand like it is little nearby to our host car. And if it is a residing is in a sense it is going far out of our point. So the residing vehicle returns a lower frequency because my radar waves will be stretching out at that point. So these are the three scenarios we can understand a basic of how the target will be understandable as nearby or far from our host vehicle. With the same speed, it will return the same frequency, so it is of no harm. And if it is approaching vehicle, our waves is compressed, so it's a higher frequency. So you should be careful, like a vehicle is approaching us and it's a receding vehicle, our frequency will be stretching out and it is out of our way. So it is of no harm again. That is the understanding from the DFFT frequency shift. And the FFT across the antenna elements. So this is for range and range rate. So it's all around the range rate because it gives the velocity between your two vehicle. So the third one is an angle, and the antenna elements what we are keeping or mounting in our car, it will give the target angle. So for multiple angles, we will be having multiple frequencies in the antenna data. So it will extract the various frequency and it will identify the angles of multiple targets. So with that antennas, it will overall environment, if I'm giving for 190-degree or 360-degree, whatever, it will get multiple frequency and it will give the targets angle for each. So as per that understanding, we can dry our car in that way. So again, the overall, as I mentioned, this is a frequency and Doppler bins I have mentioned, the range and Doppler bin. So here FFT across the samples in chirp, which means like as we are sending the chirp, as I mentioned in the previous diagram, the chirping is like a slanted lines, as I mentioned. If we are doing a FFT across the samples, each samples in a chirp, it is called a range. And that is how this is each in a range. So FFT of it's a frequency of rotation of sample phases from sample to sample, which tells us range of the target. And second one is range rate. It is across the chirp. The overall chirp, the one single chirp is under FFT, which means the range rate. It says like a frequency of rotation of range phases from chirp to chirp, which tells the velocity of the target. And another one is azimuth. It is across the antenna elements. So first we will be having multiple assigned, and again out of that we need a valid target. So with the azimuth bin, uh, as I mentioned, we will be having range bin, Doppler bin, and azimuth bin. So with the azimuth bin, which is the valid target, we will get to know. As after the full DSP processing, we get to know like, okay, here is where our valid target is present. Likewise. So this is what I mentioned in Mimic. It's a wideband integrated circuits that are often used as simple amplifiers. These are designed to replace the transistors and help the designers build the RF amplifiers. Here is where the reception part works, and the mixer and preamplifier, as we all know. Uh, Here is the transmitting signal and additional signal from the oscillator is produced, and in mixer it will be uh, uh, in mixer it will be analyzed, and the difference of it is given out as a IF signal. So this is how the mimic will work. And okay, so far as we have seen that hill, sill, vehicle, that and all the major or main testing for the ADAS software, and especially for software that includes both hardware and software, right? Here, especially for software, what are the basic testing methods to be done before handing over your software to the customer? So as in companies, we will be writing our code. It will be going through multiple level of testing. At one point, we will be having a targeted date to release our softwares to the customers. So within that span of time, it should undergo all the testing. And if in case any bug or issue is reported or identified in mid of the testings, that should be addressed and that should be clarified within the period of time of release. So it includes multiple testing methods. So out of that, I have listed these are the major things: unit testing, integration testing, qualification testing, smoke testing, chamber testing, and vehicle testing. Vehicle testing is even little later only, not while merging your code to the development or giving it to the customer. It is little later, but these are the basics just to give even your single functionality you are writing. These are the testings it should undergo before you merging it to a development branch or giving it to a customer. So the first unit testing. So as we all know, in our embedded C code or C code, C++, whatever the code we were using, for each functionality that needs to be tested, whether that function is giving or asserting, equating, whatever I am expecting is that function is giving. That is a basic uh, testing to be done. So for that, unit test is written for each functional unit of a code. It's a best practice to ensure the quality of the code, because uh, just by writing a function of a code which will not have any impact, it is like unnecessary junk which is staying there in a full big file. So the useful functionality needs a unit testing, and it helps to ensure the software is working as expected before integrating it for the major release, because the major release include multiple testing, and we should not find some bugs after multiple testing, like UT itself is failing. So it also helps to understand the logic of the code, because as a newcomer to write a code for a customer or someone, it's a very first and good task to be taken to understand the logic of the code, because for unit testing you need to know the basic of the code first, and also the flow of the code, and also how what am I expecting from it. Simply we can't write it, right? So I'm giving some input and I'm expecting some output. In a sense, that logic is understandable. So unit testing helps to understand the logic of the code. It's a major thing. And even in unit testing, automation came up in multiple ways. So automation and unit testing is done by multiple tools and scripts, which also include, nowadays we are having G-test, Google test is there. It is having a separate library. Google library is there. We will be writing and giving to Google library, and it will automatically give our analysis and reports on UT, how it covered, how much it is covered, what the standards it will compare, and it will throw errors while building itself. Such things are there in unit testing. So this is under unit testing. And integration testing is to ensure the interfaces between modules we work, and the components can communicate with each other. In a sense, as in a car, we will be working for one single module, but it has a dependency over multiple modules. So as we all know, if we are getting data acquisition from radar, it have to give the data to MCU. Okay, MCU should be there, and XCP communication should be there. Those communication interfaces and the AutoSAR stuffs. For that, we have to have the interface linkage and interface testing. So, to till my end, till the mimics end, or till the radar front end, I am giving some output, means it should reach somewhere to give the better solution. Like if I am giving a fault raised, if it is in the end of my module alone, it is of no use. It should be communicated to the next module, and it should be raised as an alarm, or it should be given as a error pin assertion, or GPIO pin assertion, kind of things to be happened, so that the integration testing is like it will test the interfaces, like whether the module also react to the input what I am providing. All the modules are working fine. Cumulatively, it's the testing. So it aims to identify the defects that could arise when the components are integrated and interact with each other. So it's like if one component is not working well, if I'm having a dependency from one component which is not yet implemented, I have my implementation ready. And if I'm trying, we will fail at this point. Okay, you're not communicating to the next component, and that is not ready. So at that point, we can request the next component to work on it and to give a code update. So that is how this will work. And it will be done for each functionalities with the dependencies of other building blocks.
उसी हिसाब से काम करना।
देखो देखो क्या हो गया
Sorry, is there any questions? Okay, let me continue. It's a test of basic testing. As I mentioned, it is not only one single test which will test all the components. There will be a multiple set of testings to be taken care uh, before merging it to the developed software. So here the CACD tools will have, but CACD in a sense, we will be having a set of things to be run, and it will have a set of requirements to pass through before merging. So it will have a mandatory requirements. First, it should go for the coverity, then compiler fixes, Then that smoke test also will be included in the CACD tools, which will all combine together before merging. Okay. And qualification testing. As we all know, QA will be there in companies. The quality testers will be there. All our audits will happen with the results of qualification testing, because the standard of a company or standard of a software will be rated with the how quality software we are providing. So qualification testing is the most important testing for the software, and the qualification metrics will be provided by the industrial standards. So there will be having a metrics, and uh, the percentage of achievements to be there, like that. How we will met, that is what the concern is. And there are functional safety measures. We have ISO standards also. Those things are to be satisfied with the test. It is not only like overall software should satisfy that, even a single functionality if we are writing, that should get a concern of everything, whether it will have impact in functional safety measures, whether it is out of our industrial standards, even it's a 5 line 10 line code. These are the things to be considered to reach out our qualification metrics to be better than others. So it's a process that verifies that a system or components meets the industrial standards for the performance and manufacturing. So it should not pass at one point and fail at later point. So it should be throughout the testing part. It should qualify every testing, and that should be considerable. So quality in the code is of multiple metrics, right? So how we are writing a code, whether it match with the if we are writing a C code, whether the MISRA rules are satisfied. Code metrics is, in a sense, MISRA rules is a set of rules we have, like how we should write a function, how the variable is to be defined, how it should be assigned, initialized. Even a small items we all writing in our code have a rules. So those metrics we have to match with. And the expected result of a component is tested against the test cases or requirements provided. So all our integration testing, qualification testings are having a defined or written test cases stored as in a as documented. So every time for multiple release, we will be doing multiple release in a month or years. So each release we have to test all our test cases written so far, and the test cases will be get updated as per our changes in a code also. So if we are simply changing our variable and not changing that variable update in test cases, that is a lag. So we will be doing all these things to ensure our code quality is fine and all our test cases are up to date and were tested properly. Next is smoke testing. It's a preliminary check. It is almost same as the integration test only. So it ensures that the software's most important function work as expected. It is a confidence testing or bill verification testing, because here is the it's kind of a overall testing where the bugs are listed out and given out likewise. So smoke testing helps to identify the major problems early and saving time and effort in the development process. So it's a, as I have mentioned, we will be having a basic bench setups where the smoke testing will be happen. It will the hardware will go through all the kind of scenarios, and there the smoke test results will give the expected results when we mount the radar in our real cars itself. So bugs are exponentially more expensive to fix in later stages. That is true, because if we are giving our software to be given for production, and it went for multiple radars, and if they find some bugs at that point, it is really expensive to fix it, because they have to clean up one whole set of radars and they have to re write it. So that's a expensive one. So the smoke testing is like a preliminary check to ensure the bugs are not there before given for the production. And the chamber testing. Chamber testing is like we will be having our software and the systems testing. So systems testing includes this chamber testing. So it is like when we go for a smoke testing, or even in the vehicle testing, if we get some issues, they will ask for the chamber testing, because there they have faced some environmental scenarios which particularly impact that or give the issue. So that scenario based testing, we can do it in a chamber. So there are multiple chambers available, like in anechoic chamber, where a radar and target are stationary, we can use and test out in a quiet chamber. And one another is, as I told, there will be a radar robotic arm which will rotate both in X and Y axis, which helps to estimate the azimuth angle. So as approaching vehicle, we can make this robotic arm as per our logged issue scenario, and we can make that robotic arm in such scenario, and we can record or test or debug the issue reported. So thermal chamber is like this radar at particular 40 degrees Celsius, minus 30 degree, minus 20. If any particular temperature it fails, it is like we will be writing a software which should be adaptable for all the scenarios. So if in case it fails at one point, particularly in a temperature condition, this thermal chambers will be used to test the software in different temperature conditions. As a supply of radars will be wide and regions. We are providing our radars for multiple regions with multiple weather conditions. So the thermal chamber is a must having test for scenario based testing. So chamber testing includes all these three: anechoic, radar robotic arm chamber testing, and thermal chamber testing. And finally, the vehicle testing. It is of it need not to be the only at the final stage of testing. Even a test vehicle in companies they'll keep for even for major releases they used to do, especially for infotainment and all. They will keep it in that system itself, and they will try that voltage related test they will do. And those vehicle testing for automotive software is a process that verifies the functionality of a vehicle software to ensure it meets the required performance standards. As I mentioned, the MISRA, AutoSAR, ISO 26262, those standards are not to be followed for a automotive industry. Those things will be verified here. This process is essential because even minor faults in software could result in a serious injury. There were news like one piece of a small piece of code where the loop was not properly handled, which leads to a biggest accident and all. Those kind of things will get to noticed only while we were doing the vehicle testing. And it's a it's a it's a well good experience to do the vehicle testing. And this test helps to log the measurements from radars, which can be used to test in case of bugs detected. Uh, sorry. What I mentioned is like vehicle testing they will go through, and there is where the real environment we will get to know. On roads we will be testing. So even the scenarios what we were testing or simulated or imaginary things we were kept before testing, no, that will all be aside. This real environment will give one another perception of to approach the software. So that kind of bugs reported or bugs detected will help to understand. With this vehicle testing we can make that scenario to happen, and we can understand by doing this vehicle testing. And as I mentioned, the way of approaching testing. In testing, we will be having signal monitoring and fault managers. It's like we will be having our signals alive. It will keep on looking for that pin to assert. Like if in case of issue, that pin will get assert, error pin will get assert, and it will be reported to the MCU where the fault manager will be there. And that fault manager will handle those things. That was all written behind the software will be there. But here, the signal monitoring, in a sense, there will be a error pin which will keep on alive to wait for that assertion if any issue is happening. So the fault injection and management is a way of testing where we'll let the system to recover automatically in case of no redundant fault. So if some faults will be there, it need not to be there to halt our complete system. If it is redundant, our system will be halt. If not, if it is a random one, which might be a false case, we can ignore and go for. So those all will be handled in software. So we will be waiting for particular time to recover automatically. We will give a reset time or delay time for it to recover automatically. And if it is not recovered at one point because of certain thresholds we will keep, Mimic will send an error signal to MCU. So the MCU is where the fault manager will be there, and it expected that MCU should take an action. At least it should say like some error data should be discarded, or completely our radar should be turned off. We should stop the system itself. So these are few fault management things. Why I have taken it in this slide is like, because as in testing, these are one another part. We have to consider the fault managers, how our signals are getting monitored and provided our signals to the MCU likewise. And there are also MATLAB automation scripts. As we were doing multiple releases, one release after release, there will be changes in the signals. Signals in a sense, the as in code, we will be, if we have rewritten the signal names or changed the thresholds, anything we have modified, like as we were working in a collaborative way, one single file will be handled by different modules. So if a signal is rewritten or corrected by another module member, he might not know. So those things have to be checked, because it should not be a ignorance which leads to a injury. So MATLAB automation scripts were used to track the variation in the signals for each release. So it will go through for all full code. It will say like, these are the signals which got changed. This is a threshold which was earlier and currently got modified in this way. This is one another approach to understand the changes over the releases. And the monitoring option is to monitor a safety sensor always, or to monitor a safety sensor only during the data acquisition period. There are certain monitoring signals which might be only at data acquisition or even till the later period. So what are the typical things we will be monitoring is supply low errors. So supply is a major thing. So we'll need the power to boot up all our components. So supply low errors is needed, and reliability related errors. The reliability related errors is to be monitored, and master clock recalibration, in a sense, all our components will be somehow uh, uh, it's like a clock ticking things only, like with the one time after time is what things will be carried over or communicated. So is any recalibration over there also monitored? And this is the another type of test, BEST. It's a built-in self-test. It's a part of functional safety. So it is like, it will automatically run within the software, and it will give us a session. So RF BIST, it's a radio frequency. RF BIST is used to identify the discrepancies between the receiver pipelines due to chip malfunctions. So chip is where we will be receiving and getting our data acquisitions. So is there any discrepancies over there? This RF BIST will identify. And if it does not meet the evaluation criteria, chip is non-functional. This is the one way to understand, like, we will be expecting the chip to behave in one way, and if it isn't, that means like it is non-functional, that needs a repair, that needs to be corrected likewise. And it also used to identify the systematic errors, random errors, and ideal time degradations. As I mentioned, the errors can be random, which will later on go off, and some systematic errors like a configuration errors and all, which needs a radiation off itself. So such systematic errors will be identified with this built-in self-test. And these are all the test setups. As I mentioned, uh, we have a basic bench setup, the debugger we will be having, through which the software will be flashed, and ECUs and harnesses will be connected, which will react, which is the miniature of the real car things we will be having. And Kano is the one which is used for that communication, XCP communication, or XCP commands, whatever we will try to induce and see the results. Those things will be do over the CANOE. It's a hardware tool. And Ethernet, we will be having Wireshark and stuffs with what the Ethernet communications will be taken care. And these are the chamber testing. Stationary ECU test will be there, and robotic arm will be there. It's an anechoic chamber where I have mentioned. Thermal chamber is for that will be separate, that to be analyzed for the temperature difference, or temperature dependent, or scenario based errors to be analyzed. And spectrum analyzer. Spectrum analyzer, as we all know, in our colleges, what we will be seeing to analyze the linearity of the power level, frequency. Here, as we are using the chirp, we can analyze here each chirp individually. What is its timing? What is its frequency? How the before and after chirps are behaving? Are we missing any chirps? Those things, it's like the spectrum analyzer will be connected to the ECU and we will be receiving the stuffs. And here we can visualize it, like whether is there any missing of data by seeing a chirp is missed, or is our chirp is not with the frequency limitations what we have provided. Kind of analysis will be happen with our spectrum analysis stuff. And test drive for vehicle testing, as I mentioned, for vehicle testing, we will be going for a test drive. And that is for hardware, around the hardware I have told. And the tools and scripts, nowadays in field, we are having so many tools widely used. It depends on different uh, customers also. Even the customers are demanding certain tools to be used, or the particular test cases should be verified in that particular tools. Kind of approach also will be there. So these are the few, it's known, and it should be understandable. And it's a flashing tool for a debugger. Jenkins, we all know. SCM is like, as I told, there is a day-to-day check-ins for the code updates will be there. Those SCM tools will be there. This is EA enterprise architecture is to whatever our software, we will be having our architecture diagrams and things stored at one tool. And Git is a common Google one, and Git test we will be using for UT. And embedded C is a script, mostly in automotive things. We will be using embedded C, and C also. C++ we will use for UT. MATLAB scripts will be used for automation and to simulation. The framework testing, those will include MATLAB scripts. CMM scripts is a one, as I mentioned, Canoi is used. There we will use flashing tools for debugger. Here we need a CMM scripts. And for Canoi tool, CAPL scripts are there. And Python automation is there for smoke testing. And Tix is a dashboard. I'll explain it later. And CACD is also, I'll explain now. So far I have explained what are the tests, started from SIL and HIL, and later how the test for software particularly it happened, like UT, IT, qualification test and all. And we have seen the hardware tools, and now the software tools I have explained. And it's a V cycle. V cycle, as we all know, if we are providing one software which developed for over a period of time, and we are giving it for production or to a customer, it should go through particular line of process, uh, development flow. It says a project management model, it's a model and software development process that uses a letter V to represent the development flow. So this is how the development flow should be. So this is a system thing. I'm being a part of software, or who are writing or updating a code, right? We will be in this end. So here we will be getting a requirements, like these are the requirements. This will be updated based on the customer input. So we will be getting our requirements provided, and as per that, our software requirements should be updated. So this should match, like system requirement should match with the software requirement. And for that, for this requirement, we should have this also should match. So SWE1 should match with SWE6. Like if we have a SRS, we should have our SQT, like software qualification test, also to be updated. Sorry. And we should have our architectural design. So if we are developing a function or a one whole file also, we should have our architectural design and our unit construction. This unit verification is our testing part, and integration testing and qualification testing. It should all go through this process before handing over it to the production. And this is a one major thing, peer review. Peer review is like uh, once we write a piece of code, it should go for a peer review. That is like our team members or the component workers or higher management. They should go for it. Should go for the peer review. It's the most efficient way to analyze, because we will be writing our code, and the bugs will be, or a change in a code uh, rules will be identified by the peers. because as we all in urge, if we do something, the peer review is a place where people will find or do the brainstorming things also, and they'll suggest and give the ideas to incorporate to improve the code. So here it helps to understand the impact of a code written in all the means, because we will write in one perception and it might not satisfy the requirement. Then the peers will give you such suggestions, and this is the process of uh, a process in a testing where we will go for a peer review. And G test. As I mentioned, unit testing, currently there are so many things. Synopsys is having a certain tool for UT, and even Eclipse we can use for UT, and G test is one among that. And Google test, it uses a C++ library, and we will be feeding our codes, and it will use a G library, and it will give up the what is the percentage of your code, whether it satisfies the evaluation properly, like that G-test will give. So it's a library for writing the C++ test, and it's a set of frameworks. So it is the automated execution. So we will be having a command as in git to commit and all, as we are having commands. For G-test also, we will be having our commands to be given for the path of the folder which we want to build. And if we give it, it will automate the test cases and it will give us the results. And this is a CI/CD, what I mentioned. It's a continuous integration and continuous delivery. As I mentioned, uh, as in market, we will be giving a multiple release to the customer. We will be having a major release later, but in between, we have to give such releases saying like we are achieving the goals in this part likewise. So it's a continuous integration and continuous delivery in a sense. Each delivery should be a quality delivery, not like simply we have to give something once the period of given time is end. It's not like that. So it's a software development practice. It isn't a testing kind of, it's a practice which includes multiple testing. So it's a practice that uses automation to improve the quality of software and speed up the delivery of updates. So it should undergo all the tests what I mentioned. So it's a process which includes all the tests I mentioned. So first, when I write the code and give it for a commit, it will go for a build first. So it's a build means normal code build. It will give for build if there is a error, build errors, like whatever the compiler we are using, if we are not given the proper code as per our compiler specific, so those build issues will be given out here. If you can, even if you can fail at this point, it will not go to the next point. So it is like a step after step. Once you pass this requirement, then you will go for next. Once you pass this, then you will go for next. Likewise, it will go until the production. So first, it will go for build and UT. As I mentioned, each function of code will undergo the UT. And integration test, as it mentioned, it includes multiple. Integration test is the component wise, individual wise, and the interface wise. All the integration tests will be here. And after all this, it will come for review. Even the CI/CD holds the requirement for review. So we will be raising it for review. We will add the peer reviewers here. So this is a point our peer reviewers will come into picture. So here they have to evaluate the things. They have to, if there is a issue they found, they will give a comment here. They'll give a comment like to improve the uh, coding standards or correcting the whole function itself. Whatever those reviews will come up here. As per that, again we have to give a comment. If we get a review comments here and it needs a correction, again we will come up from the beginning only. It will not start from next. It will again go through like everything is fine. So again the staging will happen. It will say like okay, everything is pass, and then it will go for production. So this is a uh, it can't be said as a final one. As I mentioned, vehicle testing is there, chamber testing is there, those also there. But only to stage our commits, stage our code into the development uh, space, we need these many lines to be crossed, and we have to go for a production. So this is a continuous integration and continuous delivery. So this will happen for even a minimal one line code update also. This all it should go through, and this is all to ensure the quality of our code. So it's a basic practice. And as I mentioned, this is a ticks. It's a dashboard. It's I think it's widely used now. It's a dashboard which is used for identifying the several metrics regarding the code. So as it says here, no, we will be having at the category kind of A to F, how much percentage we were in, it will say whether it is A, B, or C. And that percentage will vary for each code coverage, abstract interpretation, cyclometric complexity. Cyclometric complexity is in a sense if we have multiple if conditions in our code, like if we are simply giving if after if after if like that, now it will say like number of branches is increased, and it will give the cyclometric complexity. And compiler warnings is normally as inbuilt how the compiler warnings are there. And coding standards, uh, as I mentioned, this is a dashboard which includes multiple tools behind. So each will have multiple tools incorporated to find that metrics. So this all will go with another tool in a background. So coding standard, it will match with the MISRA C rules, and code duplication, it will see just to uh, uh, avoid the multiple line of codes. And fan out is like inclusions of our file. Those things it will go through, and it will say like these are the metrics. So here the snap, if it is 91.6, this is a place we have to improve, means again we have to go back. We will be able to see our full workspace there, and we can get in and see where exactly we are failing, and there we have to correct our issues, and again we have to go for the uh, and this particular dashboard, this will be connected to our the previous this production end. This line it will get connected to. Once it is given for production, then it will come for the ticks run. So once it gets run, and it will give out like currently the percentages, those in this way like that. Then we can check like the particular piece of code what we have provided is impacting it anyway, or it is properly giving all the scores, or it is not impacting or reducing the existing percentage. Likewise, we can check. So these are the tools and methods to test the ADAS features what we are using. As it's mentioned as testing for ADAS, I have explained you the ways of testing and types or tools or scripts to test it. That's why I didn't explain like what is ADAS or what are the features, what it is for, or how it is behave. That kind of explanation I didn't give. These are the approaches for those features to be uh, qualified to be given on road. That is how the session I have prepared, and I think I'm at end of my slide. I hope I was clear. Has any questions or suggestions?
Participants, any questions from your side, please?
I'll stop sharing. Okay, sorry. I'll keep it.
Navis ma'am, that was an excellent session, ma'am.
Thank you, thank you.
I think one person is asking question.
Yeah,
Triveni
yeah,
ma'am, go ahead.
Triveni, ma'am.
Hello, good evening, ma'am.
Yeah, ma'am. Good evening.
Ma'am, the today's session is really helpful for us for the in the research direction. May I know
Thank you.
something related the tools which you mentioned for the automation and testing. It will be helpful if you share your PPT, ma'am.
PPT is tough. One minute. I'll I'll share again.
If not,
1 minute. No, I'll share now. You can. Yeah. Is this is where you asked for. Yeah, ma'am.
Ma'am, here in this, can we run the, can we optimize the machine? We can write a code to monitor the machine optimization condition, like fault tolerance. Everything can be monitored, ma'am. Like fault
You
tolerance
mean
can
like,
be monitored using. Can we
yeah,
can we optimize
monitoring
the
in a
machine?
sense, yes. As in a tool, particularly if you are asking to visualize those, this flashing tool for debugger is where we will be using for visualizing things. So
Okay.
this is again, this debugger is particularly for the radars, not for others also. And this is a radar based one. And even TICS dashboard, I think even in service based, they were using to find the quality of, this is for quality of code. And I think this will not come for optimization part.
Okay.
Yeah.
Yeah, thank you so much.
Thank you. Thank you. Yeah. Is any more questions?
I think no more questions from the participants, ma'am.
Okay.
It was a very informative session, ma'am. Thank you for accepting our invite and being part of this program. Thank you very much, ma'am. Navis, ma'am. Thank you. Thanks a lot.
Thank you. Thank you, ma'am.
Thank you.
Thank you. Thank you for everyone for giving such opportunity. And hope it's not so hurry